Yeah, thank you. Yeah, so at the beginning, just a little bit about myself, or why do you need to care about what I'm about to say. As Philip said, I'm working at Google currently since the last year and a half. Before that in Photomath, and before that, like overall, around 10 years of experience in automation testing, also software development. Big enthusiast about everything tech and science, so trying to keep up as much as possible around everything in that area. Very keen on running, playing tennis, which I started like at the start of COVID, so that's my main pastime. And this is the photo from last weekend where I participated in the Zagreb Marathon. It was the half marathon, but still.
And you survived.
And I survived, yeah. Yeah, and I have a few disclaimers. So first and most important disclaimer is that everything I say today is my own opinion, and it does not reflect the opinions or views of my company. So that's something legal asked me to say in the beginning. The second one is that I might be rambly in a couple of bits. I'm going to try to go through it in a pace that will feel that you get the whole picture, and then we can have more time for questions maybe later, because I think it will be a question-heavy talk. And yeah, so save your questions for the end. And my goal with today's presentation is to generally just shed some light on some aspects of AI that are maybe not that visible or not that talked about much in the public eye. You hear a lot about AI hype and AI projects and stuff like that, but you rarely hear about how these models, projects are tested, and what's important when testing them, and just some terminology that will help you understand maybe why, if you send section by section, it works better than if you send like a big prompt. Hopefully we'll get to that later. So just a short primer, what are AI models? I will not go into too much depth, but generally consider them big statistical models. They're entirely based on mathematical principles about condensing data, extracting features from that data, and applying mathematical operations on a large data set, basically. You're trying to isolate features, you're trying to recognize patterns in the data, and then make some predictions or guesses around that, or trying to generate something. You go through a lot of data, process it, learn the patterns in that data, and then try to generate new data from noise, based on what you've seen before. So generally, it's statistical and really math heavy. So if you want to get into AI and testing AI, you need to be up on your math, especially like statistics. There's different tasks that models can be used for. I'll go into a bit more depth on that later. So the most important thing about models and building models, training models, testing models is data. Data is king, data is everything. And you need a lot of it to build models and train models. And the most important part about data is the labeling of the data. So it's not just enough that you have a big data set or resource. You need to actually have quality labeling of that data. So that's, in most cases, humans need to go through and add labels explaining what the data is, so that you can train a model, and then later that model can apply what it's learned and then classify, generate, or do something else with that data. Managing data, managing data sets is very important. And a big concept in managing data here is splitting data or splitting data sets. Generally, like the common practice is splitting data into 3 subsets. One is for training, validation, tuning, and test. Training, self-explanatory, you use the majority of the data. Usually it's like an 80-20 split where you use 80% of the data for training, because that's your most important resource, where you have labeled data that you just feed the model, and then the model tries to get better and better at extracting features from that model. Validation tuning is a set that's not used and fed into the training phase, but you use it for iteration and then checking if you're on the right track, if the model is going in the right track, if you're seeing outputs that you want to see, basically. And the model is not allowed to see this data beforehand. And then test comes at the end, where you have a whole separate set of data that you want to use it as rarely as possible because of something that I'll mention later. And this is also split from that other data split, you always reserve some data that the model has never seen. You never used it in the iterations. You just want to run it at the end or periodically at some bigger milestones. There's different techniques for smaller data sets, bigger data sets. Usually, if you're working in like a niche domain or something like that, you will have a much smaller data set. So you need to be really resourceful with your data, because you can't just generate endless training data. You need to be very careful. So splitting the data, you can be more creative around how you organize the data. Maybe you can add some synthetic data that you generate yourself, or play around with it, like do permutations depending on what it is, like if it's images or text. In text, you can, if you have only a set of a few thousand, you can then apply some statistical permutations where you change some word orderings or capitalization or something like that to get more randomized data so that your model can learn better. One thing I just remembered, I forgot to mention, one of the disclaimers at the beginning, I'm trying to simplify as much as possible some concepts that are really, as I said, math heavy. So some of the things might not be completely exactly correct, like if you open the Wikipedia page or something like that, nuance might be wrong, but the general idea, I'm trying to get across the general idea. So just keep that in mind. And I'll provide the references to everything I'm talking about at the end. And splitting data also depends on use case as well. The major rule is garbage in, garbage out. If you use data that's mislabeled, that has a lot of issues, lots of errors, your model will incorporate those issues, and then you'll get also bad results at the end. So GIGO is the main mantra when you're working with it. Doesn't matter how big your model is, how many parameters, how many TPUs you're using to training it, to running it. If it's bad quality data, you'll get bad quality output. So I mentioned just now how many TPUs you have. TPUs usually stand for a tensor processing unit, which is specialized hardware to run AI stuff on, because it's very expensive, so you need to specialize as much as possible. The models we are seeing lately, stuff like GPT-4, Gemini Ultra, Claude, and the rest, those are multi-billion parameter models. Those are huge. They take up terabytes, even petabytes of data in memory just to train them when you're training them. So it's very important to be mindful of the resources that you're using when dealing with those models. And it's not just the training that's really resource intensive, it's also the inference, or later when you have a trained model, then you put it into production and you perform what's called inference, where inference is actually the model then performing the task it was trained for. You provided some prompt, it generates some output. That part is also expensive, so you need to be very careful around that. One thing that's really common here is also checkpointing. Maybe you heard model checkpointing before. Model checkpointing basically means as you're training your model, you go in iterations. You go a first pass, and then you see how close you are to your expected outputs, and you try to fine tune and get to a point where you're satisfied with the results. It's non-deterministic, so it will never have 100% accuracy, but you're trying to get as close as possible to that as you can. And instead of having to run the whole training, which can take days in the very large models, instead of having to run every time from the beginning, once you reach a stage that you're really satisfied with, you take a checkpoint of it, you save all the values of the parameters in the model, save it as a checkpoint, and then you can always go back to that checkpoint, continue training from there. If it doesn't work out, go back to a known good state, and then train in a different direction, or modify the data, modify some parameters, the algorithm, or something like that. Yeah, so just to get a sense of how big they are, so this is for training operations for flops, so floating point operations. And you can see those are 10 to the power of 25, so very, very huge. And this is just in the last 7 years, I think. Yeah, 7 years. The latest models now are really, really huge. Just today I read an article that Amazon, Microsoft, and Google are looking into nuclear power to just to power their data centers and AI capabilities. So it's a really big thing. You thought crypto was bad, this is even worse. So yeah, and parameter count, so basically how many data points a model has. This is also multi-billion range, and you can see there are different. In this slide, you can see a split between different types of sets, and these others. Usually, when you see others, and these the most common are language, vision, audio, stuff like that. If you see other, it's most probably like some specialized like chemistry, protein folding, or something like that. It doesn't fall into these other ones. So yeah, differentiating models. It's very important to know how models can be different from each other. Like everybody is just saying AI models, but there's very real differences between them, how they're built, how they're tested, and so on. And one differentiation factor is on the type of training. There's multiple ways of training, like supervised, unsupervised, a combination of that. Yeah, to not go into too much details, but one general like approach between those that you can do is general models or fine-tuned models. General models are models like Gemini or ChatGPT, GPT, and stuff like that, which are trained on a huge corpus of data with the premise to be a generally good chatbot or model that can interact on a good, competent level about most topics. It isn't super specialized in one area, but it can generally provide a very good answer on a wide variety of topics. So that's general models. Of course, if you try to then do something very specialized with those models, they often fall short. That's why you use fine-tuned models. Fine-tuned models are specifically tuned for one specific area of interest, niche, use case, so on. Usually they're built from general models. So you train a huge general model, which requires like petabytes and petabytes of data, labeled data, and then you fine-tune it for a specific use case. So for example, you take something like GPT, train it to be generally very good, to have very good conversational skills, fact-checking skills, stuff like that. And then you take a specialized data set, for example, let's say from biology, and just fine-tune it on that. You need to use much less data. And then you specialize it in biology. You change a bit on the parameters, on the models, and it will use everything that it learned in the general area, and then also get the depth of a specific topic. This also means that then it will be worse at the general stuff, because you're tuning it for a specific use case, but you're accepting the trade-off. You want to, all the training before is useful to you for specializing. Then also there's types, so generative, which is basically like Midjourney or DALL-E or stuff like that, or LLMs are also generative. They generate data, basically, generate text or images, video, audio, stuff like that. Classification is they process data, so you like give them an image, you ask it, is this a cat or a dog? It gets you the answer. And this can work also on everything like text, audio, and stuff like that. Regression is that's from like linear regression. You're trying to find a relationship between data points. You feed it a lot of data and then ask it to come up with some model that represents that data very well. And what's really interesting, like ensemble models are actually a combination of multiple models under the hood. You're just like exposed to one model, but underneath the hood there's multiple models specialized in different things. And depending on what you ask it, it routes your prompt to one of the models that's really good at it, and then it returns an answer. This is really common, like if you have like some educational product or something like that, then you have a model that's really good at answering really hard questions, like Olympiad level questions from math, but it fails like really simple arithmetic problems. That's like you can use a heuristic for that, or like a heuristical model. Then you have a routing and a classificator that can classify if a problem is hard or not. If it detects it's hard, it routes it to the more advanced model. If it's an easy question, it routes it to the much less capable model. You get good results in both cases. But for example, the easier model is much more resource-friendly for hosting it, training it, and stuff like that. So you're saving a lot of resources. Then modality, I don't think I need to talk much about it. It's like language, vision, video, audio, or they can be a combination of multiple, which is called multimodal. And then, of course, based on domain. Just a quick overview of the strengths and weaknesses of like general models versus fine-tuned models. So again, training data, you need a lot of training data for general models, not so much for fine-tuned models. Performance much favors the smaller models because they're faster, require less resources. Flexibility goes on the side of general models. Yeah, so, and the application, yeah, domain specific for smaller models, general purpose for bigger models. So one thing in model testing is evaluating models. And evaluating is actually different from testing models. If you ever see like somebody talking about they're evaluating AI models or running evals on models, it's a bit different from testing. So testing is like the base layer where you test that your model is not broken, that it doesn't have any bugs, that, for example, your output is always well-structured markdown or whatever you want, like stuff like that, that the general premise works. But then evals, when you're running evals, you have a specific set of metrics that you're measuring the model performance against. So for example, an eval would be you take one of the benchmarks, like the AI benchmarks that are out there, and you run your model against it, and you eval it to see how well it performs. Like there's a famous eval, like these math Olympiad questions, like how many it can answer. That would be an eval, like you're evaluating against it. But testing is on a lower level. You're testing the basic functionality, basic premises. Here, in both testing and evaluation, two really important concepts are precision and recall. So precision is how well your model captures what you need to from the general data. This is most easily understandable for classification models. So imagine like a classifier model. Let's say a language model that tries to classify if in a sentence you use the word dog. So you have like multiple sentences, you feed it multiple sentences. Some of them might have dog in it, some might not. This model tries to find those that have the word dog in it. Your precision would be if 100% if you find all the sentences that have dog in it. If you find only like 9 out of 10, then your precision is 90%. Basically, you missed out on the one. Sorry, a bit wrong. That's you found 10 questions, but one of them was wrong. Your model made a mistake. It thought it was the correct question, but it was wrong. So that's precision. You collected 10, but 9 of them are actually true. One of them has been misclassified. So that's actually precision. Recall is the other way around. So in 100 sentences, you might have 80 of such positive cases. If you find less than that, like you return 70, then your recall is lower than 100%. You didn't find all of the sentences that exist in the overall data. And here in this chart, you can see like the trade-off between recall and precision. So you can never have 100 precision, 100 recall. That's an ideal model. Nobody has been able to achieve that unless you make some breakthrough that will be outside of the realm of possibility currently. But you're trying to reach like this spot. Like the closer you are to this spot, the better your model is, more precise and more recall it has. And usually like the F-score is used to calculate that, which is just like a mean between precision and recall. And as you can see, like as your precision increases, your recall decreases because you are more precise in what you're finding, but you're discarding some potential like edge cases or some cases that are not that clear. So you're losing your breadth, but you're gaining in the precision. So like everything that you return will be exactly what you asked for, but you will not return everything that's possible. And then this is something I talked about, like why splitting data is important. So the concept of underfitting or overfitting a model to data. These points, imagine them as data points in your training data or your eval data, and the line is what the model thinks a good approximation of it is. So if you're underfitting, that means you are not capturing the essence of the data in the model. You did not extract the features correctly. The model will feel really flaky, like all over the place. Sometimes it will get a correct answer, sometimes it will get a really bad answer, because it didn't learn the relationship between the data. It has high loss, low accuracy. And then a good model is basically as close as possible to the data points that you fed them, which means it has learned to approximate the data very well. So if you give it new data that it hasn't seen before, it can generally approximate it very well, and it can then make predictions or tasks among them. And overfitting a model is basically if you're using your test data in your training data, then you overfit the model to it. It learns very specific details about your training data. It doesn't generalize very well. And then if you apply new data to it, it doesn't know how to handle it because it just learned that specific set of data that you gave it. It performed very well on it. It's like 99% accuracy. But then if you give it something else, it drops sharply. So you want to be in the middle somewhere. So it's always a trade-off. Like same with precision and recall, underfitting, overfitting, you want to be somewhere in the middle. zero shot, one shot, few shot. So this is a concept from training, but then also you can use it like when you're interacting with ChatGPT, Gemini, Claude, or whatever other model you're interacting with. It's kind of self-explanatory. So zero shot means you're training or prompting a model without any prior context. So this means like write, let's see what a good example would be. Like write me a haiku about sports, for example, and then it will try, like from the data it has, it will try to write a haiku from sports, and models are notoriously bad at writing haiku. You will get like an average performance from that. If you do a prompt that's more like, okay, write me a haiku about sports, here's an example, and you provided an example about the haiku you want, then you'll get a much better experience, and you can try this in everything that you do. Like if you have some specific ask of it, always provide an example and see the difference between when you provide an example and when you don't provide an example. And then few shot is basically like you increase the number of examples. And there's also then a cutting off point, and the same like when you're feeding large DOMs into a prompt. Like if you gave it a bit of examples, it will perform generally very well. But if you overdo it, if you get like, I don't know how many tokens, then it will then start to hallucinate because it cannot keep track of that many data points. It just like tries to generalize too much, it will go into hallucination. So when you're interacting, like providing context or examples is always very well. That's always why model, especially chatbots, perform better if you phrase it as like, you are an AI researcher, you're trying to figure out X thing. Here is what you need to do, instead of, hey, how do you do X thing? It will perform better if you like put the role on it and explain a bit of context, give it like a scenario. Yeah, and a few closing remarks. So this is also one fairly recent study that's really interesting. So if you're being nice in your prompt to chatbots, like if you use please, thank you, and nice wording, you'll get better responses in general. Doesn't matter what area, what expectation, you'll get better responses. And it's also true because of the underlying data. Because if you just imagine like it's trained on internet data, if somebody is behaving rude on the internet, they will get like a short, snippy reply. If somebody is really friendly, they will usually get a much better reply, which means more data for the model to train in, which means better result in the end.
So it wasn't trained on Stack Overflow data.
Sorry? This is a big one. So our intuitive thinking is like models are reasoning, models are thinking, and you try to like personalize it, and like, oh, how did it come to that conclusion, or how did it write this in this specific way? It acts like a human or something like that. Especially like if you're classifying images or generating images or stuff like that. But they are just statistical models. Like there's nothing magic going on underneath. Okay, you don't know what's going on, but it's just really advanced math because it's a black box. But it's like it doesn't reason. It does not have the capability to reason currently, as of yet. So a bias is a reflection of human bias. So like when you get like experiments like Microsoft's Tay, Twitter bot, I don't know how many of you are familiar, they released a bot on Twitter, and within a day it became like fascist and started spewing fascist remarks. So that means a lot of the data that was coming in was also of that kind. So if you have some biases in the output, it most probably bias in the input, and also humans generate a lot of biases. Like also a famous example, which is like an image classification, is when Microsoft was working on face recognition for unlocking laptops. It famously didn't work for darker colored people because the engineers that were designing it didn't think that it was important to include that data in the training set, so they trained on pejorative white people, so it didn't work as well. Yeah, more data doesn't always mean better results because all of the things I mentioned before, like labeling, splitting data, organizing data, all that plays much bigger importance than actually just like increasing the number of data points. And AIs can hallucinate. Like the worse they are, the more they hallucinate. The more complex tasks you give them, they hallucinate more. And generally, like the bigger prompts, they also hallucinate more. They just invent stuff that's most probable, that they know from the training data. Again, they're just next word guessers. Like LLMs, all the chatbots are just guessing the best next word. It has some advanced math, to understand some context in the sentences, what you said before. But generally, its only task is what is the best next word I can put in the output to generate a response. So always keep that in mind when interacting with it. Yeah, and here's all the references. So everything I talked about is in these links. Yeah, and I think we have a few minutes for questions. So that's it.
Can you please just return the slide garbage in, garbage out?
Very funny. All of these images that you saw, except the graphs, I used Gemini and ChatGPT to generate them. This one it just couldn't do. Like I tried Midjourney, tried DALL-E, tried it. Like I just described, like generate me an image for a slide about to talk about AI that talks about garbage in, garbage out. Just generate like super awkward like stuff, like graphs or like actual garbage trucks, but like nothing. I tried like 15 times. I ran out of tokens on ChatGPT.
Did you say please?
Yeah. I said, you are giving a presentation. Generate a slide for yourself.
Any questions? It's one question. So thank you for the presentation. I just don't get actually what do testers at your company do. Like, I see how models generally work. I see that you need to have test data, which I will guess developers will run. But what actually testers do for AI models?
Yeah, so I can only talk about generally, like what would the role of a tester be in an AI product? Well, it's checking the quality of the data. So you're stepping back from actually automating web pages or something like that. Your main concern is the quality of the data going in and also the outputs. But then you still have like a lot of the general quality stuff around it. So like you always will have a UI for your AI product and stuff like that. But specifically about AI, the job of a test engineer working in that is to make sure like that your premise is good, like the split of the data is good, that your labeling is good. Like you send out a data set for labeling, you get it back, you don't know if it's good or bad. You need to like have ways so that you can extract a snapshot of it. For example, like out of a data set of 100,000, you need to find a way of taking a representative snapshot, going through it, and evaluating, okay, was the labeling good? And then once you get like a subsample, then you apply to the general data set. You say like, okay, I had like 70% of the labels were good. I can extrapolate on the overall data set that maybe like the accuracy is, I don't know, like 65%, 60%. You take some measures, biases, and stuff like that. So it's really in that area. But then also creating tools for faster testing. And for testing like prompting and stuff like that. Like you're not for enabling developers to test their iterations faster, basically. So you're switching more into the area of like enabling testing and making sure that all the testing that has been done is good and like follows good practices. Because yeah, developers can test and a lot of developers test good, but all of you have experiences where a developer writes a test and it's testing nothing, or it misses the point. So it's always important to have a person with a lot of experience in testing provide input in how something is tested. I hope it answers somewhat.
Nice presentation. I would like to ask, as from my point of view, that I have worked with ML and AI on major corporation with colors from USA. And I would like to ask what kind of tests do you perform as a QA engineer and what kind of tests does developers perform?
Mm-hmm. Yeah, so developers are focused more generally on the immediate stuff. They're training iterations, and they need to make sure that when they train new iterations that it's going in the right direction. So they're preparing tests that check basically trend lines and progress in that area. But checking end-to-end quality falls in the QA area or quality assurance area, where you're not so deep in the details of tuning parameters, hyperparameters. You're taking the general experience. I construct a general prompt, and by the product specifications, I expect an answer. And then you run it through and see what you get. But you're not just running one or two. You create a data set, eval data set or test data set, and you need to curate it and make sure like that you capture edge cases or like cases like this where there might be some bias or some miss, like a hole in the data that you want to check against. So you construct those data sets, then run it against the model where like, okay, one part is the construction of the data set, the second part is writing all the infrastructure of interfacing with the model and tooling, and then you evaluate the results, where you need to be really careful and familiar to check that the output matches what the product specified. And since it's not just like a blank web page or web page with some structured data, it's kind of always something new. You have to establish like metrics that you track your quality against. So you cannot just have like a pass or fail. You always have some gradation or like a percentage number of how good you are. And the ideal is like some, I don't know, 99% or something like that.
So basically you are a data scientist?
Somewhat, yeah, but more focused on like data scientists. Yeah, it's kind of blending, yeah, but there's a lot of data handling and preparation.
Okay, thank you.
So one question, because all these are huge models, you said that you need a new power plant to run them. What is the chance of somebody taking a 70 billion parameter model like Olama, like some kind of open source, and creating something that's specifically for their needs, right? What kind of, in your opinion, what kind of team would they need, or what's the end cost, I think, to establish it on your project, let's say?
Yeah, you need to buy a lot of GPUs first. That's the main point, or TPUs if you can get your hands on.
Yeah.
But yeah, that's the difference between general models and fine-tuning models. You need to have a lot of resources to train a general model, but a small team can take something like Llama, which has like I don't know how many billion parameters already pre-trained, and then take it and specialize, like just do fine-tune training, specialize it on one area that you're interested in, that you want to create a product for. And that's much, much cheaper. You still need graphics cards, you still need AI engineers, data engineers, stuff like that, but it's much cheaper. I can't say of a figure, like I never have done that.
Yeah, but how many people would you say like?
Yeah, like generally, like the point where it's now, there's so much infrastructure around it. Like you can run a lot of these things on like all the cloud service providers. Everyone has their own AI set of features, so you can do a lot of stuff that you would previously have people. I would say like a few people, like under 5 or 5, can do. But then again, you still need like a front-end guy, a back-end guy to tie everything together to do a good UI for it. So, but for AI engineers, like 1 or 2 really good AI engineers can handle something like that, I would say.
Any more questions?
It was great, he's a very good guy, and that's all, nobody is Niko.